Good morning, everyone. We are into, I think, sixth class. Probably this is the sixth one. We're into sixth class, and the date is 17th August, right? This should be 2021, day 6. All right. We are into our business. I have given few books name here. You can look into them. Bayer and Johnston, the McGraw-Hill. That is one of the reference book you can use. It's a very good book. In the sense, a lot of problems are solved. A lot of problems, a bit different from Hibbler. A little bit thought-oriented problems. Then there is this one. This one is very good one. You can try this. Madhukar Vable, which you can take, has his book as a soft copy online. That means that's a very good book. It explains a lot. A lot of different mechanisms in details. Okay, so it has a lot of examples, a lot of good short questions, objective questions to make sure that you understand the concept well. Concepts is very well cleared in this book, but it's a big book, and a lot of things are there which is outside the syllabus. In the sense, this book is not for strength of material only. It's a little bit advanced kind of book, but all the concepts of strength of materials are covered in it, so you will get everything there. And it's a good one. There are a lot of examples are solved in that. Okay, so that's one. Then Hibbler, obviously, I'm using Hibbler to explain a few things. And examples are taken from Hibbler. As and when I'll take examples from Hibbler or Bayer and Johnston, I will write that it has been taken. Jay, the screen can probably lag a little bit because the network is not so good, from last few days in IIT. They say that there is a drag in NKN network. So could be, So I'll go slow, okay, if it helps. So Hibbler is one that we are going to follow most of the part of the course in the beginning. And then obviously, as I said, NPTEL lectures from Professor M.S. Sivakumar. That also you can follow. So mostly these are the three books, and this is the NPTEL lecture. So this is available free on the web. This is also available free on the web. Okay, one version of it. So you can take help of those things. Today we are going to discuss on mechanical stresses, a very important concept for mechanical engineers. And I think we started discussing this in the last class. And we say that apart from humans do feel a lot of stress when there is a lot of work they have to do. These are mental stresses. Physical stress can come if you have to work a lot with heavy weights. In that case, you can get physical stress. This is a muscle-based stress. What we're going to talk here is mechanical stress that the materials follow. Okay. Now, when humans follow stresses, as I was discussing last class, every human is different, right? And therefore, every human will have a different capacity of bearing stresses, and they will do it based on their own, genetic, physical, other kind of biological criteria. But when I talk about materials, I would expect that every material, not every material, one material, if I talk about a particular material, and if I make structures based on that material, they should always have something in common, right? So when I test, because I cannot test every one material, every structure, right? So if I make a bar with one, let's say with iron, and then I make a circular sphere with that iron, and then I make a cube with that iron, or let's say I make a tree out of that iron, okay? I should not expect that the iron will fail differently for these different structures, because I cannot test all the four structures. I will test probably one of them or a sample of them, one sample of it, and say that this is its capacity, right? I cannot say that four different things have four different capacity and therefore I have to test them. Then, in that case, everywhere, every structure that you build, every aeroplane that you build, every mechanical car that you make, or probably any mechanical equipment, machine that you make, have to be tested. And if you keep on testing, then you lose a lot of time first, then you don't make also, right? You keep on testing. So we need to find a standard. How is that standard found is what we're going to discuss here. So that's standard comes from the stresses. So let us consider a prismatic bar. When I say a prismatic bar, it means it's a bar of uniform cross section. Okay. So let us make a bar of uniform cross section. Let me draw with the blocking. Let's say it is fixed at this end and the bar is like this. When I say a bar, please note, when I say a bar, it means it has only axial loading. Okay. So let's say I have given an axial load P here. So if I draw its free body diagram, it's going to look like this. P, right? Let me give a few properties to this bar. Let's say that its cross-sectional area is A. Okay, its length is L. All right, very nice. So far, so good. Now, if I take a section here, what I'll get? I'll get two sections, right? So one section will be from here to here. Now this side is P, so this has to be P. Similarly, there will be another side, which is this. Since this is P, this has to be P, right? Now, let's try to understand here that this part of the cross section, this end of the cross section, there is a P force by, let's say, if I have something here, it is given by that. Okay. And this side of the P on this very end is also given load, right? But this cross section, let's say, let us name this cross section as AA dash. So this cross section AA dash is an internal part of the body, right? This is an internal part of the body. Now, when it's an internal part of the body, I have no idea whether this force is going to be a single force or it's going to be distributed like this, or it's going to be distributed like this, right? Because that's internal force and I do not have any way to measure it right now with me. So what I will do, but it has to follow an equilibrium, right? Body cannot move, body cannot rotate. So therefore the force is known, that's going to be P, okay? But the distribution of force is not known. But I know that summation of all that forces comes here, small, should add up to P. Okay. So what I say is instead of finding forces at every point, what I'll do is I'll try to find something called stress, which is sigma equal to P over A. Okay. That means I'm dividing the force into the area divided by the area that is available at that cross section. So by that area here. Similarly, here also I'll do the same. Sigma is going to be P over A. Okay, that's how I define my stress. So this is called stress. So sigma is called stress, and its international symbol is sigma, and its unit is force per area, right? Newton per meter square, which is also called Pascal, not megapascal, which is also called Pascal, as in Pascal, P as in Pascal. Okay. All right. Now let's say this is the maximum force that it could carry. Okay, P. Now, if I have a similar structure here, but with double the cross section. So this is L, but this is 2A. Okay. In that case, what we have, and it is acted. So if the area of cross section is double, what would be its maximum capacity? Maximum capacity will be 2P if for the small one the capacity is P. But let's say there is only P force that is acting here. Instead of P, let me write it P dash. Okay, and this is 2A. So its sigma is going to be P dash by 2A. Right? Now, if I look at ultimate capacity, the maximum capacity of the structure, and if I define that is sigma max or sigma ultimate, let's say, then this should be constant for the material, whether I am making it for a cross section of area A or a cross section of area 2A. This should be property of the material. In the last class itself, we discussed that when you have a chalk, when you have a wood or a member made up of bar, of steel or any metal, right? You need little force to break a chalk, you need little higher force to break a wood, and you need lot more force to break a steel or metallic bar of same length and size, right? That comes from the material. And I would expect that even if I make shorter and shorter the length of the its capacity of the wood or the chalk, its capacity of carrying maximum load may be different, but something has to be kept constant. That something is its carrying capacity, maximum stress carrying capacity. Okay, we'll talk about this maximum stress carrying capacity maybe in a few more classes from here. But this is what makes each material unique in its properties. So if the stress for a material is understood as a bar example, we will now go and define it more mathematically in a better way. So before that, let us take, that was for a 1D problem. This is a 1D structure, right? This is a structure which is one-dimensional. A bar is in one dimension. That means it acts with only one direction of force is acting on it. There is no two direction of force, right? Now let's come to another object. This is a general object. You can see a general 3D object, and there are a lot of loads acting on it. P1, P2, P3. They are in different directions, and there is a distributed load also acting on it. So now I am interested in taking a cross section AA from it. Okay, so I'm taking a section. Please note that I'm taking a section, and this can be an imaginary section also. Okay, so if I take that section, what it's going to look like is something like this, right? It's going to look something like this. Oh, copy, let's say. And if I put it here, what do I get? Nothing. I don't get anything. Anyway, so let me try once more. Screenshot. Then go here, copy, paste. Wow, that's good. That's good. So the free body diagram is going to look like this, right? And let me rub all the forces that, oh, this is a screenshot. It will not rub. Yeah, so so if I look at this part of the cross section, so that's going to look like this. There is a P force here, P1 force, and there is a distributed P force here, right? Now, the body has to be in equilibrium under this force. So therefore, the cutout portion that I had, the cutout portion, which is something like this, right, with P2 force, P3 force, and P4 force. All right. So that part will act some force, on the body. So some reaction force. This is called internal force. We know that. So that internal force is given by, let's say, this some F, delta F. So this delta F is the internal force that we have. Now, if you look at the body like this, if you look at this plane that we have, that plane has an angle, right, with respect to horizontal. Okay, so that's this plane also. So we take a small square area or a small differential area within that plane, and that differential area is written as dA. Very small differential area, okay. Now there can be one force, so the resultant force that is acting is del F like this, okay. That can be taken as two components. So this was your del F that was working on the plane. There was this plane, right? Or let me draw it a little bit differently. Okay, let's say this was the plane, and del F is working like that here from this point A or C. Del F was working like this. Now, this orientation of the plane can have two things. One can be, I'll first show it. One can be normal to it, outward normal to it, and one can be along its surface, right? Okay, so I can draw this force as two components. One is normal to it, which we'll write it as delta Fn, and one that is grazing the surface, which we will call at delta F surface. So delta F is taken into two components. One is, so I'll write that, delta F is resolved into two components. One, normal to the plane section, right? AA. Okay. And second, along the surface. Right? So I get one is delta Fn and one is delta, this is delta Fn and this is delta Fs. Now both the forces I can divide by delta area. So now, how do you do it? So first is you locate a point, as I did, we look at a point on which you want to find the stress. So let's say we want it at C. Assume a differential area. First you take a section from that point, so you take a section from that point. Assume a differential area A delta S around that point. So you assume a very small area here. For the point, in 3D, assume differential volume. So if it's a 3D, then you have to assume a differential volume. It's a 2D, you assume a differential area. Each surface of the volume will give you an area to calculate, This is area. All right. So we'll discuss this more. So don't worry about it. So right now we have this. Now how we calculate stress is we call sigma n, let us name them, sigma n as normal stress and tau as shear stress. Okay. Now sigma n normal stress, as I say, it should be normal force divided by the area. So sigma n is normal force divided by area with a limit that area going to 0. So it's not only divided by area, you have to make a limit that area is tending towards 0. Similarly, shear stress, whose representation is tau, is given as the grazing force, the force that is grazing the surface, so delta Fs divided by delta area. Okay, please note that area is same because whether it's normal or it's grazing the surface, the area over which I'm looking at, it's same. All right, so tau represents shear stress. We call it as a shear stress because it tries to shear the surface. You might have heard it in fluid mechanics, the shear stress, the shear force. So when I say shear stress, it's like something that is grazing the surface. Okay, and then the normal force is something that goes out of the surface normally. So you can see from this figure, delta F is grazing the surface. Okay, so it will try to move the surface along this direction. And normal is that is acting like this, which is trying to pull the surface to outward, right? So these two force I have divided into, and then I found the stress by dividing it by the same area, okay, over which it acts. So the area is the the area is the area over which the force is acting, okay. So for shear stress, it used to be area over which the shear stress is acting. For normal stress, it has to be the area over which the normal stress is acting. So this is how your shear stress and normal stress are defined. So there are two kinds of stress, okay. One is shear, the other one is normal. Please never forget this. One is normal, the other one is shear, okay. There are no other kinds of forces, stresses. So while doing this, we did a few things. So just to summarize what we have done, one is we have taken a limit here, right? So when I'm taking a limit, I'm assuming that delta AF is continuous over delta area, okay? They're continuous. So delta AF is continuous over delta area. That's how I can take the limit here. And that continuity is going to be maintained as long as I don't go to the microstructure of the material. If I go to the microstructure, then it becomes discrete, right? There is no more continuous because you are looking at element by element. In the sense, you're looking at atom by atom or molecule by molecule. In that case, or microstructure by each of the microstructure by microstructure. In that case, these definitions may not prevail. There are a few major characteristics of the stress. When you define a stress, you first define it at a point. Remember, we don't define stress over a surface. We don't define a stress along a length or something. We define a stress at a point. That's why it's called state of a stress at a point. The definition itself is state of a stress at a point. So we define stress at a point upon an imaginary plane. Okay, so this is the imaginary plane. Then when we cut it, we saw there is a 2D surface here. And on the 2D surface, we put out a point C, and that C point we found the stresses, right? The physical dimension of stress is Newton per meter square or Newton per millimeter square. It can be pound per square inch, anything, but it has to be force by area. The stress resultant is resultant of an internal force generated by one part of the body on its counterpart. So if you look at here, these are the forces, right? These are the internal forces that are generated by the other part of the body, right? Which was here, like this I have drawn this example, right? Yeah. So this part of the body has acted these forces on this part of the body. So it's an internal force divided by area. It's not an external force. Okay, so please note these things. Do not make mistakes here. Okay, stress is represented by coordinates. Okay. Now there are two things that, yes.
Hello.
Yeah.
The shear stress should be the normal stress is a single direction, but the shear stress can be any direction along the plane, right?
Yeah, I will talk about that a little later. Right now you assume that you have taken a component, one along the surface, one along the normal. Okay.
Okay.
Right. That's what you assume right now. We will discuss this in another few slides. You are very right. This ASS can be taken along any direction. We have to make sure that we mention the direction. We'll come and tell that. So right now I'm assuming that there is only two division. One is along the normal and only along the grazing surface, any direction in the grazing surface. Okay. The magnitude is going to remain same as long as you have only one. The stress resultant of the internal force generated by one of part. Okay. The stress is represented by coordinates, two coordinates, not one coordinate. It is represented by two coordinates. As now you have understood by this, by the discussion that we have, and by the question that was asked, is when I take a force, I can take along either normal or the gauging surface, right? But when I take a stress, I'm dividing it by the area, right? Now, area is considered based on the direction of the normal. So I can take, this as my area, okay, and that will be defined by its normal in. Then I can take another area which is like this, and that normal will be defined by something this, right? So if you change the direction of area, the component of force has to change along the direction of the area. Or when I say direction of area, I talk about the normal to the area, right? Normal to the plane of area. it will change. And if the force change, then that force divided by the area will also change. Therefore, it depends on two things. One is the direction of the force, right? The other one is the normal to the area. Okay, so there are two things that are needed to define a stress at a point. One representing the direction of the force, whose resultant is the stress, and the other one representing the normal to the plane on which the stress is acting. Okay, and that's why, as the question asks, that you can take component Fs or delta Fs in a particular direction. We have to do that. We have to take it in two directions, one along, if you say x, the other one along y, right? And then we have to say that the forces along y and x will be divided by the same area, but they will be different because they're two components. And therefore, you have to mention which direction you're looking at. So two things, one is the force direction and the other is the normal direction of the plane. Okay. Okay, let me make it a little bit more clear, in this. So when I took this Fs, so this was my surface area. Okay. Let me draw the normal with a blue chalk. This is the normal n. And along the normal, there was Fs, right? So let me go to some other color. Yeah, along the normal, there was Fn. This is delta Fn. But there was something called Fs, right? Let's say Fs was this. Delta Fs. Now, delta Fs will be divided into two parts. One should be like this, along this maybe. So I'm drawing it coordinate axis like this, right? So draw it bigger. Let's say these are my coordinate systems. Okay. So I have to divide this Fs into these two parts, right? Let's say this is x and this is y. So I will have delta F is along x and delta F is along y, right? Now, when you call about delta F is stress, so delta F is x divided by same area, and the other one is delta F is y divided by same area. But there are two different directions, right? One is along x direction, one is along y direction. Now, what does this S represent? There is this S also which represents it. It represents the surface. Surface, which surface it represent? How do I mention this surface? I can mention this surface only by its normal, right? Because I said an area is defined, the direction of an area is defined by its normal. So I have to tell that this F is along a norm perpendicular to this N, right? So the area. So it has to come as, let's say the area is normal is N, then this has to be represented as, let's say this is sigma. I write them as sigma. This is sigma x n, and that should be sigma y n, right? Now that n has come from, as you know, now n has come from the normal to the surface, right? Okay, so that's how it is defined. Generally, it's not defined as this. It is defined as first comes the n, then comes the y. Then here also first comes the n, then comes the x. It doesn't matter because they will be equal. So it doesn't matter. Okay, so this is how it is defined. But in case of this normal force that we had, the direction of the force, so direction of the plane is n, right? And direction of the force is also along the normal, right? So that is delta Fn by delta A. So this is called Nn. So all the normal forces are always of same, notations. They are either xx or yy or zz. All the shear stresses will be of different, indices. This will be xy or yz or zx. Okay, all right. So these are called normal forces. They are normal force. Normal stress, sorry, not force. And these are shear. So when I call it shear, so please note, when I call it a shear, I cannot use sigma. Many people use sigma. I would rather use tau, because we represent shear as tau. So I'd rather represent tau. Okay. All right. So there are a few things to note. One is you have to understand which is the direction of the plane, and the second, which direction is the force coming from. And then both of these will represent your stress direction. Okay. So we talked about what is stress, and we looked at stress at a point. Now, when we gave this example of a normal stress, so of in a rod, right? When we talked about a normal stress in a rod, we showed this example, and then we took a component section here and showed that this section has a force. How do you guarantee that the force on this cross section is going to be same when I wrote P by A? Remember that I'm using P by A, I'm not using the limit here. Okay. Generally, when you calculate in your strength of material, you cannot use that limit. You just know the area. Unless I give you as a functional form, you cannot take that limit. Now, this cross section may have force, stress distribution like this. Something like that. Okay. I don't know. All right. What happens is, what we do is called average stress. Okay. So this is called an average normal stress. And instead of taking the limit, I defined it sigma average is P by A. Okay. The units remain same. The definition is it's not stress as a point, it becomes an average stress over that cross section. So it's an average stress at that point. It's not the actual stress. Okay. All right. Okay. So similarly, you can have average normal stress, average shear stress also. The force acting at the central line of the body, centroid of the cross section, is called average stress, average normal stress. The section considered is a bit far from the boundary. So this section is when it acts like this portion, you can talk about average stress, not on these boundaries. So wherever the force is acting, so for example, I think I have images for that. Yeah, there are images for that. Yes, there is image for that. So no worries about it. I don't have to draw. And you assume that the material is same across that cross section, because the material change, meaning the stress carrying capacity will change. Orientation of the material will change. So for a normal stress area, cross section should be normal to the force of the free body diagram. So when you talk about normal stress, we have already defined for a normal stress, the normal has to be along the direction of the force, right? Or the force has to be along the direction of the normal. That's what is normal stress. Now, as I said, if you have a force P here, it's going to be same P dash, P dash, P dash, P dash. Okay. So if you have this force here, so it's the same bar drawn vertically. So there is a compressive force P dash here, and then there will be a compressive force P dash also here, right? If you take very close to this surface, whenever you're giving force, there will be an instability at that point. There will be a huge stress at that point. Okay, that's why if you see that when you want to break a concrete or a very hard surface, you start making a small hole, right, with a chisel and a hammer, and it slowly, so it first chips off from that joint itself where you are hitting, right? If you take a nail and hole a wall also, you will see that it makes a hole only around wherever the nail is. So the stress is high at that point. Okay, so that's what is going to happen. You will get a high stress at that location where the force is. Right? But if you go down, the force will gradually disperse like this. And after a certain time, your stress is going to be almost uniform. And that uniform stress is what is called average stress. So therefore, when you look, we don't look very near to it. We look a little bit far away from the points where the forces are acting, as well as far away from the joints. Something like this also will create a problem, because there is a sudden change in cross section. So the force flow will definitely be higher here, and then it will be average, and then here suddenly it will change again, right? So these are the sections where there will be less forces. So this sudden jump will create a stress concentration. Okay, so we'll talk about that a little later, but these are the points which will not have an average stress. Okay, there will be some stress concentration that will come in, and you have to multiply with the stress. But the objective is overall summation of all the forces along the subject, so summation of all stresses along the cross section over the area is going to be same as P force or average force into area. Okay, so that's the bottom line. So, in a sentence, if you want me to ask you, so all in this course, you will mostly follow average stress. So you don't have to worry about whether you are looking at the joint, looking at a point near the force, unless it is specified in the problem. It's always that average normal stress that you are going to consider. One small example before we finish this class. Please see there is a rod here. Okay, this is a rod because we are looking at axial force. Okay, so it's a bar. It said it's a bar. A bar meaning axial loading. Okay, please note that, don't forget it, unless specified. All right, so the width of the bar is given, it is 35 mm, and its thickness is given 10 mm. Why is the width and the thickness given? To find the area, right? So the cross section of the bar is going to look like this, whose width is given to be, oh, thickness is smaller than width. Okay, my diagram is not commensurating. Okay, so this is 35 mm and this is 10 mm, and it's look like this. Okay, so that's the cross section. So I'll color the cross sectional part. Color is not good, it's not visible. So this is my cross section area. So area is given, right? So area we can calculate from that, and the force diagram is given. 12 Newton here, and there are two more forces acting at 9 Newton, 9 Newton, 4. So two more forces are acting at 4 Newton opposite direction. And you see, you don't have to consider the area here because they are only to give force. Okay, they have been given just to make sure the force can be attached there. Right? There is a 22 Newton force here, 22 Newton force. The whole body is in equilibrium. You have to assume that the body is in equilibrium. Okay, what do we do? We have to first find, so you see that the stress depends on the internal force, so we have to find internal forces. We cannot calculate stress based on the external forces that are given here. We have to know what is the internal force acting here. So to find internal force, what you have to do first is we have to take free body diagrams here, take section here, take section here, take section here, and draw free body diagrams, right? So let's do that. So we have taken a section here, we have taken a section here. Okay, so if you take a section here, this is going to how it's going to look like. There is a 12 kilonewton acting here, right? And this section, I don't know what is the force I have to calculate. So what is going to be? It's going to be in equilibrium, right? So again, equilibrium kicks in. Okay, conditions. So if I kick it, yes.
Sir, the whole structure will have some acceleration, right?
If there is an unbalanced force, yes, it can have acceleration, but we are assuming it's to be static.
So like there is 21 kilonewton along left and 26 along right. So like
Yeah,
some
then
of it will be used for acceleration and some of it will be like in the form of stress, I thought.
No. Unbalanced force is always for motion. Okay, not some of it, some of it. Unbalanced force gives rise to motion. Balanced force will not give rise to motion. All right.
Okay. Yeah.
So understood?
Yes, sir. But over here, like it will still.
But it looks like balanced, right? It's not balanced.
Oh,
so 9
okay.
plus 9 is 18 plus 12 is 30, and this side it's 4 plus 4 8 plus 22 is 30, right? Both are 30.
Oh, I thought it was just 9. It was just 9 kilonewton and 4. I didn't.
Or yeah, that might be a it's not maybe clear from the picture, but there are two force directions. That
Okay.
means there are two force notations. So that means there are two separate forces. Okay. So if I take a cross section at this point, and if I draw a free body diagram, so this side is going to be 12 kilonewton. So let's draw. This is called axial force diagram. Please note, you have to draw axial force diagrams for this. You have not learned that in your engineering mechanics. Now you learn it, how to draw axial force diagram. You have learned DMD. This is AFT. So this is my full length of the structure. From here to here, it's the same cross-sectional area, and there is no force acting in between. So whatever be the force here, internal, they all be same all through, right? So this is going to be, it's 12 all through up to this, right? Then you take another cross-section here between B and C, and you know that 12 kilonewton is acting this side, 12 is acting this side, 12 is acting this side, and then this side it's going to be 9 plus 9, 18 plus 12, it's 13. So, and now you see the direction of the force is very important. So it's going acting outward. So that means it is pulling it outside. So it is tensile force. We call them tensile. Pulling outside is tensile. Okay. This is also tensile. So it's going to be in the same direction. So my top part is tensile. Bottom may be compressive. So this is my 0. All right. So now I can put it up to 30. And then the 30 continues till this point because there is no force between this and this. 30 continues till this point. And here, if I take another cross section, it has to be equal to 22. So it will come down to 22. So this is your active force, axial force diagram. Now, based on this axial force diagram, we have to find the stress. So stress in this portion of the body is going to be the internal force at that portion of the body divided by the area. Area is same. So I can just divide by the area. Similarly, stress at this portion is going to be the internal force at that portion divided by the area, where it's same again, and stress at this portion is going to be internal force divided by the area. But also mention, note that the direction of the forces are very important. Here also it is tensile because it's going out of the body, right? It's trying to pull the body on both sides. So it's also going to be tensile. So that calculations are done here now. You can see the calculation. So this is going to be 12 by 350 is the area. That's going to be 30 by 350, and this is going to be 22 by 350. You can do the calculation at your home in your calculator. Just some calculations are given. So this is your axial stress diagram, which almost going to look like axial force diagram. Since area is constant, okay, looks similar to axial force diagram as area is same, right? I have given a small note here. Please, use it. Units. Okay. What happens if you have 1 Newton per millimeter square? You can write it as 1 MPa also. Okay. 1 Newton per meter square is 1 Newton per meter square is equal to 1 Pascal. Okay. But 1 Newton per millimeter square becomes equal to 1 megapascal, because there is a 10 to the power 6 multiple. Okay. Generally, unit of stresses in structures, most of the general structure that we use, general, not heavy, are given in units of MPa. Okay. So the building that we're right now sitting may have its concrete strength around 30 MPa or 35 MPa or 25 MPa. So they are in units of MPa. The steel rebars that you have inside, they may have the strength, ultimate strength at 415 MPa. Okay. The design strength may be 250 MPa. So those things are given in MPa. So generally, whatever you see around you design structures, they will have units only in MPas. So if in engineering somebody asks you in your in your core interview for job, somebody asks you what is the unit of something, okay, in stress, the stresses will be mostly in MPas. So it can go 30, 40, 50 MPas, right? Maybe 100 of MPas, 200 MPas. Don't tell them that it is in Pascal. Okay. So they will be in terms of 10 to the power of 6 Newton per meter square, not in tens of Newton per meter square. It will be in 10 to the power of 6 of Newton per meter square. General material, unless there is specific things, right? There are high strength materials. There are very low strength, material. For biological materials, will have very low strength, Newton per meter square in those cases, but general structure I'm talking about will have stresses in MPS, but the stress carrying capacities will be quite high. Okay, so the calculation is continuing. The calculation is given here. You can go through. It's simple. Force is this, cross section is this, so sigma is this. Tensile because the force is tensile. Okay. In this case, you don't have to write two justification for sigma because we are calculating normal stress, and normal stress is always along the direction of the force because the area of cross section normal is also along the direction of the force. So sigma in. And then you can calculate which section will be more. So you know that this section is going to have more force. Okay. All right. So there is another international standard that any tensile is given as positive and any compressive is given as negative. So this is positive. This is negative. This is an international standard, and we have to follow this in our course also. Okay. So whenever the stresses are drawn outside of the cross section, they are called tensile stress. They come because of the force that are outside. Whenever a stress arrow is drawn towards the cross section, we call it compressive stress or raised due to compressive force, and they are considered to be negative. Okay, with that I'll stop today. This is the final answer. The maximum stress is here. With that I'll stop today.